Hello everybody and welcome to our next unit, or next video rather, in unit 6, which we're going to look at the energy of phase changes. So in this thermodynamics unit, okay, we've been looking at heat in particular. So there's some change in heat that's associated with chemical reactions. And there is also a change in heat when we are dissociating certain ionic materials into water, which we saw in the last video. And we can calculate that value by using calorimetry. And you've done the heat of solution virtual lab at this point, and maybe a lab in class, depends on timing. But there's also energy that's associated with phase changes, which we have to learn about as well. So as we're changing phase from a solid to a liquid or a gas, or whichever way you're going, there's some heat that's either absorbed or released. So not only is heat absorbed or released when changing the temperature of material, there's a significant amount of heat that's absorbed or released when a material goes through a phase change. So also with calorimetry, we looked at energy that must be absorbed in order for a certain material to raise temperature, or there must be energy that's released when it lowers in temperature. When we go through phase changes, there's also a change in the amount of energy those particles have. So just to refresh your memory, though I'm sure you remember, solids are very, very, very close together, and they take the shape of the container that they're in. We say that solids will have vibrational, I'll just put VIB here, vibrational energy. And if we put this, let me draw this a little bit nicer. So I'll make a solid over here in a beaker. And here's my beaker. My solid will be very tightly packed towards the bottom, and it doesn't take the shape of the container that it's in. That's a terrible drawing, but I think you get the idea. Let's see if I can draw this a little bit nicer. There we go. That's a little bit better. Retains its shape, and they don't take the shape of the container. Liquids, on the other hand, they have vibrational energy, but they also have translational energy. And translational means they could slide past each other. So liquids have more energy than solids do. So if I consider what a beaker of a liquid would look like, they're still very close together, but these particles will be slightly farther apart, and they take the shape of the container that they're in. Okay, I was actually asked recently, I guess there was something going around on social media, that peanut butter is not allowed on a plane because it's considered a liquid. And they're like, why is peanut butter considered a liquid? And if you think about it, peanut butter takes the shape of the container that it's in. So I guess TSA considers peanut butter a liquid. Now, do I consider peanut butter a liquid? Probably not. But that's the definition of it, so that's what they go by. Gases, on the other hand, have even more energy. So they have vibrational energy, they have translational energy, but they also have rotational energy. So if I were to draw what gas particles look like, these particles are very far apart relative to their size. If you remember the kinetic molecular theory, they're in constant, rapid, random motion. They hit the walls of the container. There's no net loss of energy. But gases have a lot more energy than solids and liquids do. So in order for us to change phases to go from a solid to a liquid to a gas, so if I'm going in this direction, we have to absorb energy. I remember phase diagrams from Chem 2. So I have solid, liquid, and I consider this gas, not vapor. So I think of slug going straight across. We have to absorb energy going from a solid to a liquid to a gas. But if I'm going from a gas to a liquid to a solid, these are releasing energy. So if you consider what type of process would be, if I have an ice cube that's melting, that ice cube has to absorb energy. So therefore, that is an endothermic process. Endothermic process going from a solid to a liquid to a vapor. If I'm going from a vapor to a liquid to a solid, so if I am freezing ice cubes, I put the ice cubes into the freezer, that would be an exothermic reaction. Not a reaction, an exothermic process. It has to release energy in order for that to occur. And something to keep in mind is that on here, you'll see that there's a pressure of 1 atmosphere. This is what we call the normal pressure, and normal is just, standard temperature or standard pressure, right? So 1 atmosphere, we consider the normal boiling point or melting point, and that's because that is at 1 atmosphere. So if we consider here the normal freezing point of water, we know to be 0 degrees. Now that changes depending on elevation. Or the normal boiling point of water we know is 100 degrees. But again, that also changes due to elevation. So if you are higher on top of a mountain, there is less pressure that's being exerted on you. So if the lower the pressure, that actually means the lower the boiling point. And we talked about that more in Chem 2, and so we're not going to talk about phase diagrams here because actually you're not assessed on phase diagrams. But I wanted to show you that we do have to absorb energy or release energy through these processes. And there's a value that we can define that tells us how much heat energy is lost or gained to go through these phase changes. And the first one is the heat or enthalpy of fusion. And in Chem 2, we did talk about this. Now, some classes in Chem 2, remember, it depends on how much I focused on thermo. I know some of you did see quite a bit of this. So the enthalpy of fusion is the amount of heat energy required to melt 1 gram of a substance at its melting point. And there's a certain value that's associated with that, right? And we're going to take a look at some values here. So the equation for that is Q equals M times the enthalpy of fusion. So it looks very similar to Q equals MC delta T. But in this case, I have this whole new thing. This is one thing right here. Okay, and that's the enthalpy of fusion. And fusion typically is the value that tells us if I'm going from a solid to a liquid or if I'm going from a liquid to a solid. Okay, where M is the mass, which is consistent, and that delta H of fusion is what's the value or how much heat must be applied in order to melt 1 gram of something. And it's going to be different depending on the nature of the material itself. So let's take a look at an example here. So I have ice going to water. So I'm changing its state of matter. I'm going from a solid to a liquid. And it looks like here my enthalpy of fusion is positive 335 joules per gram. So this is positive 335 joules per gram, or sorry, joules per gram, not mole. This means that per every 1 gram of water, 1 gram of ice, I would have to input 335 joules of energy in order to melt that much ice. So melting water is an example of an endothermic process. I have to put energy in. That ice has to absorb that much energy in order for this phase change to occur. Now, of course, the higher the mass of the sample, the more energy it would take. If Lake Wallenpaupack is frozen, it's not going to take 335 joules of energy to melt the lake. It's going to take whatever mass the lake is in grams and multiply that by 335. So that's basically the equation we have here, is how much heat is required to melt some sample, depending on its mass, times its enthalpy of fusion. And if I look at the opposite reactions, the opposite process, so if I have liquid water going to solid, if you remember Hess's law, right, if I flip that equation, that means my sign for delta H also changes. So here, I would release 335 joules per 1 gram of energy. So freezing water is an example of an exothermic process. And that's because heat must be released in order for this reaction to occur. This is how we would calculate enthalpy of fusion, okay, or how much heat is required to melt or to solidify something. We would use this equation here. On the other hand, it looks very similar when we consider vaporization. So going from a liquid to a gas or a gas to a liquid. And this is what we call the heat or enthalpy of vaporization. So remember, it's the exact same thing, but we're just considering a different state of matter here. So let's get the right stuff here. The heat or enthalpy of vaporization is the amount of heat energy required to vaporize 1 gram of a liquid at its boiling point. Now remember, we could use heat or enthalpy of vaporization to say, okay, how much energy is needed to vaporize it. But really, if we switch the sign, it also tells me how much heat is released when I condense 1 gram of a gas into a liquid. So, and that's what we're trying to demonstrate here, is that when I flip this process around, that sign for delta H changes. So let's consider here. Same exact equation. Okay, the only thing you're changing is this value, because remember, this delta H of vaporization depends on the nature of the material itself. That includes intermolecular forces and all of that. So it's a little bit different, and you'll be given that value. So for example, if I look at these two equations down here, vaporizing water, which is what this is showing here. So if I go from liquid water to gaseous water, if I'm boiling water, I have to input energy. When you put water on the stove to boil it, okay, you have to turn the stove on. You have to add heat to it. So this value is positive. So vaporizing water, again, is an endothermic process. I have to put energy in to that. On the other hand, if I'm condensing water, so if I'm going from gaseous water to liquid water, that is actually releasing the same amount of energy. So this would be plus heat as a reactant, but the opposite direction, my heat would be a product. So remember, I'm just switching the value of, or the sign of delta H. Condensing water is an example of an exothermic process. And I think that makes a lot of sense based on what we've talked about with Hess's law. We're actually not going to do any practice with these in here because we're going to do practice with those in class. But anyway, let's take a look at some heating curves. College Board loves a good heating curve and explaining the heating curves. So the amount of energy that's associated with a phase change depends on the nature of the substance. For example, the type of intermolecular forces, bringing it back to Unit 3, type of intermolecular forces that are present between the particles. So if you look at water, okay, water has an enthalpy of vaporization, a heat of vaporization of 2,260 joules per 1 gram. So to vaporize 1 gram of water, you would have to input 2,260 joules of energy. Why so much? Why does it take so much heat to vaporize 1 gram of water? Well, as we know, water has pretty strong hydrogen bonds that are between them. Not only does it have 2 sites for hydrogen bonding, but oxygen is also quite electronegative. Other than fluorine, it's the most electronegative element. So this has the ability to hydrogen bond with other nearby water molecules. These are hard to break. It takes a lot of energy to break those hydrogen bonds. I have to break them in order for these particles to become a gas because they have to separate, right? They have to become very far apart. So every hydrogen bond has to be broken. Ammonia, notice it has a much smaller enthalpy of vaporization. So why is that? Yes, ammonia can still hydrogen bond. There's its structure. But it only has 1 site for hydrogen bonding. So I'll draw a little hydrogen bond here. Oh gosh, there we go. I'm trying to draw this as best as I can. So there's an H right there. But this hydrogen bond's a little bit weaker than this one. So we'll say this one's weaker. Why is that? Because nitrogen is not as electronegative as oxygen is. So that's a slightly weaker hydrogen bond. Hydrogen sulfide does not have the ability to hydrogen bond. It is a polar molecule. So if I draw H2S, highly polar, experiences dipole-dipole intermolecular forces of attraction. Even though this is polar, those dipole-dipoles are not nearly as strong as those hydrogen bonds. So it does not take as much energy to vaporize 1 gram of hydrogen sulfide. Look how we're going down. Diatomic hydrogen, even less than that, barely any energy is required to vaporize that. That's why it's already a gas at room temperature. It already has the amount of energy it needs to vaporize. And that's because diatomic hydrogen only experiences those London dispersion, intermolecular forces of attraction. So if we remember back to unit 3, actually, so what would we say about the enthalpy of vaporization for diatomic chlorine? Would it be higher or lower than hydrogen? Should be a little higher than that. Chlorine, even though it's nonpolar, has London dispersion, intermolecular forces of attraction, but those London dispersion forces are a little bit stronger than they are for hydrogen. And that's because chlorine has more electrons, which, remember the phrase that we use? What do we say? This has a more polarizable electron cloud. That's because it has more electrons. Diatomic chlorine, one side of this could be more negative than one side of this. Okay, that's kind of like a throwback to unit 3. Anyway, there's different values for enthalpy of vaporization. That's what I wanted us to get from that. And it all comes down to intermolecular forces. So here's a heating curve for water. Okay, so when I'm starting off with ice, which is down here, so I have ice at negative 25 degrees Celsius, ice. And we know the normal melting point of ice is 0 degrees. So I see here that ice is going to raise its temperature until it gets to its melting point. So right here, I'm raising the temperature of ice. Once it gets to its melting point, however, look how the temperature is constant. The temperature stays the same, right? Once all of that sample has melted, then once I get all liquid, all that liquid starts to raise its temperature again. But once I get to that boiling point, notice, holy moly, look at this line, right? Really long line going across. And once all that vaporization is still happening, once it's over, we can raise the temperature of that gas again. I want us to take a look at this. And I believe I talked about this in Chem 2, not 100% sure. Again, it always depends on the semester. But let's analyze this heating curve for water. And here again, it shows us what's happening. So step 1, the ice is warming. All have that ice particles that are gaining temperature. At point 2, I have some solid that's present, but I also have some liquid particles that are there. Okay, so I have a sort of, I don't want to say equilibrium, but I have both of these that are present in the container when it's melting. At point 3, I have just liquid water. At point 4, notice that I start to have some liquid water, takes the shape of its container, but I also have some gas that's present. And remember, that gas will exert a pressure on the outer portion of the container, which we call its vapor pressure. And then, of course, everything will be vaporized there. Let's answer these questions. Consider the heating curve for water above. Why does the curve plateau at points 2 and 4, even though heat's still being applied to the system? So it does say heat added. And as I am melting this ice, I'm still adding heat. And as I'm vaporizing this water, I'm still adding heat. Actually, holy moly, look how much heat I'm adding. Looks like about 15 kilojoules per mole to about 55. Looks like I'm adding about 40 kilojoules to vaporize water. So what's happening, right? Where's that energy going if it's not going towards raising the temperature? That energy is going towards breaking the intermolecular forces. So at point 2, I have to break these hydrogen bonds. That's where the energy is going, even though I'm adding heat. For part 4, that energy is going towards breaking every hydrogen bond to get this water to vaporize. So that heat is breaking some intermolecular forces, some IMAs that are needed to change phases. So it's going towards breaking all those intermolecular forces. It's not going towards raising the temperature or raising the kinetic energy. We have to break all of those intermolecular forces or some of the intermolecular forces during a phase change. Question 2 is asking, why is plateau 4 so much longer than plateau 2? So if I notice, I have to input a heck of a lot more energy to vaporize water than I do to melt water or to melt ice, okay? We can compare the enthalpy of fusion. This right here is my enthalpy of fusion versus my enthalpy of vaporization. I could compare those values by looking at a heating curve. So plateau is so much longer because it requires more energy to vaporize water. Than it does to melt it. And you can even qualitatively figure that out. This looks like it's from about, I don't know, maybe 1 to 7 or 8. We'll say about 7 here. So about 6 kilojoules is needed in order to melt water. However, we need 40 kilojoules. So if you consider that, nearly 7 times more energy is needed to vaporize that sample of water. Because again, I have to break every single hydrogen bond. Do lines 1, 2, and 3 have the same slope? So I'm going to erase some stuff here so it's a little bit easier to see. So now we're going to compare the lines 1, 2, and 3. We've already looked at points 2 and 4. So here's 2, here's 4. That's done. We're looking at 1, 2, and 3. Do they have the same slope? So right here, here's ice. Raising the temperature of ice does not take a lot of energy to raise the temperature of ice. If I look here, this slope is still pretty steep, but it looks a little bit more broad. This line is much more steep than this one. And this line also looks very steep, okay? So do they have the same slope? No. And the question is asking, what does that say about the specific heat capacity for each phase of water? Because this slope is very steep and this slope is very steep. So we'll say 1 and 5, these have the steep slopes, steepest slopes. This must mean that we do not have to add nearly as much energy to raise the temperature of that particular phase of matter. It takes much less energy to raise the temperature of ice and to raise the temperature of water vapor than it does for liquid water. So here, if heat's on my x-axis here, I have to input more heat to raise the temperature a certain amount, okay? So 1 and 5 have the steepest slopes, and because it takes less energy to raise the temperature of those phases of matter, this must mean that their specific heats are much smaller. So we're going to say lines 1 and 2, or lines 1 and 5, I'm sorry, are the steepest. This tells us that the specific heat capacity of water vapor and ice are smaller than that of liquid water. So we can compare a specific heat capacity by looking at the slope of the lines. It takes more energy to raise the temperature of water, liquid water, than it does for ice and water vapor, which means the specific heat capacity must also be higher. Let's take a look at this next page here. So, last thing, here's a very generic heating curve with equations when performing calculations. And I don't think you're going to have to use too much of this, right? Because quite honestly, I think they just want you to get one equation down. They would never ask you like a 5-step question like this. I would do that in Chem too, but they actually, I'm pretty sure they don't do that in AP Chemistry. So anyway, if I'm going from ice to water, so here's a very generic heating curve, and this is ice and all that, but you can use this for any substance. All right, any substance here. Okay, so if I'm going from ice to water to steam, I have to input energy. So this would be an example of an endothermic process. Whereas if I'm going in the opposite direction, this would be an example of an exothermic process, releasing energy. If I'm in the solid state of matter, so we're just going to say solid here for this. If I'm raising the temperature of a solid, I would use the equation Q equals MC delta T to figure out, okay, how much heat is required to raise the temperature of the solid if I'm not going through a phase change. Use Q equals MC delta T. If I reach that substance's melting point, I would use the equation Q is equal to M times the enthalpy of fusion, because that's going to tell me how much energy is required to melt this sample. Okay, so we would use this equation to figure out what's my value here. And delta H of fusion, remember, is positive or negative depending on which direction you're going in. If it's endothermic, it would be positive. If it's exothermic, it would be negative. So that changes the value of heat. If I have just liquid here, so if I have a liquid and I'm raising the temperature of the liquid, but I'm not going through a phase change, I would use the equation again, Q equals MC delta T, to calculate what is the heat energy that's absorbed or released when I simply change the temperature of a liquid and I don't go through its phase change. If I have a phase change, if this is between a solid and a liquid, this guy's between a liquid and a gas. So if I am changing from a liquid to a gas, I can calculate how much energy is needed to undergo that process by using the equation Q is equal to M times the enthalpy of vaporization. Okay, very similar to the enthalpy of fusion. I'm just changing the constant, whatever the value is for that substance based on intermolecular forces. Finally, if I have a gas, and if I'm raising the temperature of a gas without going through a phase change, I would use the equation again, Q equals MC delta T. Because again, I could change the temperature of a gas or a liquid or a solid because I'm not breaking any intermolecular forces. There is no temperature change during the phase change. So there's no temperature change here, and there's no temperature change here because you're breaking intermolecular forces. That energy is going towards breaking those forces. That energy is going towards breaking those intermolecular forces rather than actually raising the temperature. So when I'm in the solid state, when I'm in the liquid state, when I'm in the gaseous state, I can raise the temperature. So it's a raised temperature. So that's why we have a delta T for that. Anyway, we're going to do some practice with this in class. So I know there's no sample problems on here, but it keeps the video nice and short. And remember, some of you definitely have done this before, which is nice. Makes it a little bit easier for you. Otherwise, we have one more video left in Unit 6, and that video is going to be on enthalpy of formation, and we're going to look at some bond energies there, and I think you're going to find this very easy as well. As always, if you have any questions, let me know. Otherwise, I will see you on in that last video in thermodynamics very soon. Bye.